To understand the bottleneck in arid land restoration, we have to look at the chemistry of the topsoil. In these degraded environments, the accumulation of natural bioavailable nitrogen and ambient soil moisture requires decades of undisturbed biological activity. That slow accumulation is actively reversed by extreme dust events. The sheer mechanical force of these storms strips away the minimal organic layer before the soil can stabilize. To bypass this timeline, planetary engineers have proposed the Dust Nova framework. It leverages a cyclical flow of matter between the troposphere and the ground to force ecological recovery within single seasons. The system operates through three precise mechanical interventions: lofting-engineered bioaerosols, steering atmospheric plasma, and deploying bioreceptive ground gels. This is structured as a conservative, testable architecture. Every phase is governed by strict measurement, reporting, and verification protocols, and gated by specific technology readiness levels to ensure environmental safety. Dust Nova shifts ecological restoration from a passive biological waiting game into the active management of a high-energy, cloud-to-soil bioelectronic circuit. The first intervention is the Dust Bio Seed. Tethered balloons loft an engineered payload directly into the turbulent inflow of an approaching storm. This payload blends pollen carriers, fine biochar, and microbes with high ice nucleating activity. In the cloud, they act as highly efficient nucleation points, causing supercooled water to freeze at much higher temperatures. This alters droplet interactions, directly localizing rainfall over the targeted basin. In parallel, the particles act electrostatically. Swept upward, they undergo intense triboelectric charging. This artificially raises the local electric field strength within the storm updraft. To mitigate the risks of introducing airborne particulate matter, the payload is co-formulated with Centella asiatica liposomes, which suppress the release of respirable aeroallergens. System guidelines require verifiable data showing that these liposomes suppress free aerosol acids by at least 70% before any deployment can occur. The resulting bioseed acts as a dual trigger mechanism. It forces early, localized precipitation while electrically priming the atmospheric boundary layer for the active operational phase. With the cloud seeded and the electric field elevated, the system transitions to the spark-morph reactor. Ground stations monitor the highly charged conditions overhead. When the thresholds are met, terawatt lasers fire from the ground directly into the storm inflow, carving conductive plasma filaments through the sky. These lasers do not initiate the storms. They simply establish a path of least resistance, steering naturally imminent electrical discharges toward engineered target zones. The primary mathematical metric compares a randomized scatterplot of natural lightning to a guided cluster terminating on a central receptor. To pass the deployment gate, the laser must increase the probability of a targeted strike by a delta greater than 0.1. When a guided strike connects, it drives an immediate high-energy chemical reaction. Ambient atmospheric nitrogen is oxidized by the plasma heat into reactive NOx compounds. This atmospheric NOx immediately dissolves into the enhanced rainfall from the bioseed, raining out of the storm column as highly concentrated nitrate and nitrite. Current orbital measurements indicate yields on the order of 100 to 400 moles of reactive nitrogen generated per single guided flash. Combining thermal precipitation forcing with laser guidance, Dust Nova turns natural lightning into a precision electrochemical tool, delivering in-situ nitrogen fertilizer straight to the exhausted topsoil. Generating atmospheric nitrogen is useless if the sheer energy of the delivery mechanism sterilizes the ground. To capture the pulse, the target zones are pre-treated with a mycoquartz gel. This gel operates as a living receptor. It contains pyrophilus, fire-loving fungi, and sulfur-oxidizing bacteria, organisms biologically adapted to rapidly metabolize charred material. Supported by the biochar ballast from the bioseed phase, these microbes secrete specific organic acids that mobilize essential heavy minerals, such as raw potassium, elemental zinc, and calcium from the fresh ash. However, the localized lightning strike creates an extreme hazard, a massive spike of reactive oxygen species, and a severe acidic pulse at the termination point. To prevent total soil death, The gel is embedded with pH-responsive Centella asiatica enzymes. When the acidic pulse triggers a sudden drop in pH, the liposomes rupture, instantly flooding the termination point with antioxidant molecules that neutralize the incoming ROS radicals. Finally, the treated area is stabilized by a sprayable living crust, an algal and moss binder known as the PMMB green sheet, which seals the captured moisture and nitrogen into the soil matrix. The success of the ground layer is measured against strict hypotheses, achieving a 40. The dust holds more charge, systematically lowering the laser energy threshold to initiate the next discharge. Because this modifies wide-scale weather patterns, operations must submit to an open measurement, reporting, and verification protocol. Validating these atmospheric shifts requires orbital infrastructure. Teams track aerosol optical depth via the MODIS instrument and utilize geostationary lightning mappers to verify causal inference between the laser operations and precipitation patterns. Over successive seasons, DustNova builds a self-optimizing feedback circuit. The chemical output of one engineered storm actively programs the bioelectrical properties of the next. Testing the extreme boundary limits of this engineering requires examining its potential on Mars. Translating the system to the Martian surface introduces severe environmental constraints: a thin 600 pascal CO2 atmosphere, intense UV sterilization, and strict COSPAR planetary protection rules that forbid any live biological payloads. To model this, researchers use Earth-based analogs in the Antarctic dry valleys to test completely sterile variants of the architecture, replacing the active microbes with inert mineral ice nucleating particles and synthetic biochar. Because the low nitrogen Martian atmosphere prevents Earth-style oxidation, the target shifts. Electrostatic discharge biasing is instead used to harvest and mobilize native nitrates already trapped within the Martian regolith brines, a purely abiotic method of in situ resource utilization. Whether deployed to rapidly recover Earth's degraded dust belts or to synthesize critical resources on the Martian surface, treating the atmosphere and the soil as a singular, programmable electronic circuit provides a tested mechanism for planetary-scale ecological engineering.